Okay, we're trying to discuss the two fluid from a quantitative point of view. But before we go on to that, since you have not done courses in hydrodynamics, yes, apparently, it's just remind of some. Let me discuss a very basic thing in hydrodynamics, which is basically the form that Newton's second law takes when you have a flowing fluid. So if you have a fluid and you follow a small volume of the fluid, so after a time, since the whole thing is flowing, it will end up somewhere here. Okay? So if you want to talk about how various quantities are changing between this region and this region, this derivative, del del t, will simply not work, right? Because what does del del t really do? The rate at which something changes when you do not change x, y, and z. Of course, that means that if we were to look at the contents of this particular volume here, just focus on this particular volume and find out how some physical quantity pertaining to volume changes time, that will be described by del del t. Is that okay? However, you should also realize that the fluid was flowing actually has moved somewhere else. So it's now here. What here at some t at t plus it's not the same volume, it's in a different place. Okay?
স্যার আপনার কথাগুলো খুব কেটে যাচ্ছে।
আচ্ছা, কানেকশনটা একটু গন্ডগোলে খুব বাজেভাবে কাটছে কি?
হ্যাঁ মানে মাঝে মাঝে একটু কেটে যাচ্ছে।
সেটা একটু আগে সহ্য করতে হয় মনে হচ্ছে, কারণ আজকে এখানকার কানেকশন আবার সারাচ্ছে। Okay, if you give me some time, let me just try one thing. I will try to see whether I can connect to the sender and work. If I can.
স্যার এখন শোনা যাচ্ছে।
শোনা যাচ্ছে? ঠিক আছে, তাহলে থাক, আপাতত এটা কাজ করছে, এটাই থাক। যেটা বলছিলাম সেটা হচ্ছে you are focusing on a particular volume of fluid, which means that as time goes by, it's not a fixed volume in space. As time goes by, this volume moves somewhere else. Okay? So if I want to talk about how some physical quantity pertaining to this volume is changing, del del t will not really be the appropriate partial derivative or appropriate derivative to take. Because del del t only talks about what happens here at time t versus what happens at the same place at time t plus delta t, right? And talks about the difference. But what we really want to do is follow the fluid element around from here to here and figure out how some physical quantity has changed. Does this make sense? Say, for example, if I start with velocity of the fluid in here and multiply that by the mass of a fluid particle, it looks like we are going to get the force, but we are not going to get the force this way. This is not, although this is mass times acceleration, the trouble is I'm not really interested in the velocity change inside the volume, because at time t some fluid particle was here. At time t plus delta t, that fluid particle is somewhere else. You have some other fluid particle here. So when you do v at t plus delta t minus v at t to find out the change in volume, you are actually subtracting the volume of this fluid particle, which was here at time t, from the velocity of this fluid particle, which is a different fluid particle at time t plus delta t. So this difference is not really what we want to talk about when we talk about acceleration. When we talk about acceleration, it's really this particle, which was here at time t, has moved here at time t plus delta t. We want to figure out the rate at which the velocity of this particular particle has changed. Is this okay with everybody? This physical concept is the most important part here. The rest is straightforward.
Yes, sir.
So, if you really wanted to figure out how much the velocity has changed, you would have to take this, which is the original. So this is r, the position vector of this cube. You want to take the velocity of a point particle or an atom or a molecule in this volume at time t. And what you should do is subtract that from the velocity of this particle, which is the same particle, it has just moved at a different position at time t plus delta t. But what is this different position? This is no longer r, right? But how much has the part fluid moved between t and t plus delta t? This much, right? And that's nothing but the velocity into delta t. Is that okay? So this new position is r plus v delta t. Sorry. So what you really should do is figure out what is the velocity of the fluid at r plus v delta t at time t plus delta t and subtract these two things. This minus this will give you the change in velocity of that particular fluid particle. Divide that by delta t, you're going to get the acceleration. Are you with me so far?
Yes, sir.
So in general, I've just pointed out the velocity. It could be any function of position and time. So any function of x, z, t, something which relates to the fluid which is flowing. For this, the appropriate derivative, if you want to do it correctly, should be this. You subtract the original value of f. I'm going to write the symbol on this side later, but what you should do is x plus vx delta t, y t plus delta t. Similar things for y and z. Y plus vy delta t, z plus vz delta t. And time t plus delta t. And divide this whole thing by delta t, the time interval, and take the limit as delta t goes to 0. Okay. So this is a kind of derivative, but it's a different kind of derivative from the kind that you're used to. And it's written often in this with this symbol, t, capital D by capital dt. And it's called the Eulerian derivative, simply because Leonhard Euler talked about this in some detail in his treatise on fluid law. It's also called the convective derivative, simply because motion of fluid particles as time goes by, that's exactly what convection is. And this derivative differs from the del del t because of this motion of the fluid. So this has nothing to do with superfluids or quantum mechanics specifically. This is basic hydrodynamics. Any physical quantity pertaining to a moving fluid whose rate of change you really want to take a look at, the appropriate derivative to look at would be something like this, the Eulerian derivative. And of course, you can rewrite this in terms of ordinary derivatives. Why? Because all these functions changed, right? Why is that? Why is it changed? Because the variables have changed. So how much is this new value? It's basically f at x plus. So let me just write this out separately. What we have is f at x plus vx delta t, y plus vy delta t, z plus vz delta t, and t plus delta t. And how much is more than f of x, y, z? That's the question. And the answer is all to do is use Taylor series. So if you are doing Taylor series in multiple variables, you have 4 variables here, x, y, z, and t, and you are doing a Taylor series in all of them. And the answer is pretty straightforward. The first order change in the function is simply rate at which the function changes with each of the arguments times the change in the argument. So because the t has changed by delta t, you should have del f del t delta t. That's because t has changed. But also x has changed. So you should have del f del x, right? Into the change in x, which is vx delta t, plus del f del y, vy delta t, plus del f del z, vz delta t, right? Of course, this is only further there are delta t square order terms, higher order terms. Okay? But when you subtract fx, y, z from this, you're left with this plus order delta t square terms. To divide that by delta t and then take the limit delta t goes to 0, all these order delta t square terms vanish. So what you are left with is the following. So is this clear to everybody? This is going to be central to what our next step is going to be, or what we are going to actually find out later. Clear?
Yes, sir.
And there's a compact way of writing this, which is, of course, you can write this as del del t plus v vector dot del acting on L, right? V vector dot del is vx del del x plus vy del del y plus vz del del z. Okay? In particular, the acceleration term for a point particle moving in a fluid would look something like m dv vector dt, and that will be m del v del c plus v dot grad v. And note that this makes life a lot more complicated than for point particle mechanics, because in point particle mechanics, the acceleration is linear in the velocity, right? It's just dv dt. And if you change v to twice v, the acceleration just doubles. Here, on the other hand, you should notice that this term is still linear in v, but this term is actually quadratic in v, right? You have 2 v's in this, being in a sense multiplied. If you double the v, the first term doubles, the second term becomes 4 times bigger. And that makes fluid dynamics a lot more complicated because it's inherently nonlinear as compared to classical mechanics of point particles. The reason this quadratic term is also very simple. After all, the amount by which the fluid flows or moves depends on the velocity. So you're finding out the rate of change of velocity, but you are actually evaluating it at a position which is already further away by a term which is proportional to the velocity. That's where this v squared term comes from. Okay. So this was basic hydrodynamics. We will equate this to the force acting on the particles to figure out the law of motion for a fluid. But that is going to come later. This is just review of hydrodynamics, because we will get an equation which will look very much like this, which will help us interpret the resulting superfluid flow as that of a flow of a fluid under a special kind of force. In fact, under no dissipation whatsoever. But that will come later. But we will need to be able to identify that term when it comes to us. So this is why we need to actually remember that this is what the mass times acceleration term looks like when you're talking about a fluid flow. Once again, let me stress, this has nothing to do with superfluids in particular. It works for all fluids. Okay, is this clear so that we can move on to the next topic, or move back to the previous topic to be more precise? Yes?
Yes, sir.
Okay, so let's move back to the question about quantum mechanics of a superfluid. Remember, we said that a superfluid will be described by one macroscopic wave function. This is only for the superfluid part of helium-2 below transition. Above transition, above 2.7 Kelvin, superfluid, there are no superfluids atoms. That is, you have helium-2, you have below 4 Kelvin, you have a helium-2 liquid. Sorry, you have helium-1 then, not helium-2. And in helium-1, you do not have any superfluid component. In helium-2, a part of the molecules or atoms, after all, they're the same, they become, they go into a macroscopic quantum state. Not all of the atoms, a fraction of the atoms. Those are our superfluid atoms. And they are described by this particular wave function, which we talked about the last day, Psi0 RT. And we have already talked a lot about the fact that the current here essentially is Psi0 square H cross by M grad theta. Which is N times the velocity of super. So this is a superfluid current, of course. And it's the number of superfluid particles times Vs, and Ns essentially is Psi0 square. So we interpret Vs as H cross by M grad theta, and the fact that that leads to a super irrotational flow and the notion of vortices, etc. We have already discussed that in some detail. Now, what we are going to focus on today is the fact that this wave function is supposed to obey a Schrodinger equation-like equation. It is supposed to obey IH cross del psi del T is minus H cross square by twice M Laplacian psi plus a effective potential into psi. Let me remind you once again that this is an effective potential because in a true quantum mechanical picture of this system, you should actually talk about a multi-particle wave function which depends on the coordinates of each particle. And the potential, of course, will be the potential of interaction of each particle with each other, with every other particle. What we are doing here is we are replacing that by an effective single particle approximation, which is you essentially treat every particle as if they are moving according to the Schrodinger equation, or they are obeying the Schrodinger equation, corresponding to a potential which is an effective average value of all the other potentials exerted by every other particle. And what we wanted to talk about is exactly what this potential is going to be like. And for this, let me just think of it, talk about a particular simple physical situation. Let's say you have a superfluid, a body of superfluid which is maintained at a constant volume, and there is no entropy exchange with the outside world right now. But in this body, let's say that some superfluid atoms moves from a region A to another region B. So this is what we have here is helium-2, which has both normal atoms and superfluid atoms. And we are just asking what would happen if a bunch of superfluid atoms move from here to here. Now, one very important thing that you have to bear in mind is if this happens, the superfluid atoms will all be in the ground state. They will not carry any energy from one place to another. Okay? Overall, the energy of the system will not change. But what is the energy of this system? It's basically a sum of two terms. One is the energy of the fluid, which is at rest, to which you have to add the energy of the superfluid atoms, which are now moving from one place to another. So this energy, of course, depends on the momentum of these superfluid atoms, and the momentum is also related to this K. This H plus K is basically the momentum of the atoms. Okay. So this is the quantity which should actually not change. This is U, the total energy. Okay. But now that actually means the change in the total energy will be change in U0 when N, say, let's call that delta N superfluid atoms move from here to here. And this has to be 0. Now, this fluid at rest, we had already figured out what happens to that when you change the number of particles in that, right? We know that du0 is TdS minus PdV. That's mu dn. And so when what you have done here is you have just moved delta n number of superfluid atoms from here to here. And for that, the relevant thing is to look at what is the rate at which this energy changes when you change n. So what is that? That's simply mu, right? So here, what will happen is delta USK is a change in, so the superfluid atoms here had some kinetic energy. That's exactly the energy of the USK here. And when they get to B, they have possibly some other kinetic energy. The kinetic energy can very well change when you move from one place to another. So delta USK, this change, plus the change in U0. That's what you have to look at. And what is the change in U0? Simple. The change in U0 is there because at A, you're losing some delta in number of atoms. At B, you're gaining them. Let me point out one thing very clearly, or one thing which should be very clear here. The superfluid atoms and the normal atoms together make up helium-2. So when you say U0, you're talking about the internal energy of the entire helium-2 liquid. Okay. From that one part, the delta N superfluid atoms has moved from here to here. In the process, they have lost some kinetic energy perhaps, or gained some kinetic energy when they have moved from here to here. But what is that change related to? That's related to this delta U0, which is nothing but delta N. Now what will happen? Number of particles into the rate at which U0 changes with particles, right? So what will you do? At B, as a result of the process, what has happened at B? The number of particles is increased by delta N, right? A had these delta N particles, they have moved to B. So at the point B, there has been an increase in energy U0, which is given by del U0 del N at constant entropy and volume, because that's the condition we have at point B, right? But B has gained particles, A has lost them. And because A has lost particles, you should have this. Is this clear?
Yes, sir.
And now, this tells you the delta U, the change in the kinetic energy. So this K is basically there to indicate that this is the energy due to the momentum. This is basically kinetic energy of the superfluid. How much is that going to be equal to? Or delta USK by delta N. The change in kinetic energy of superfluid atoms per atom is simply going to be minus this quantity and this bracket. Now, what is this quantity? Mu at B, and this is mu at A. So when superfluid atoms flow from A to B, the kinetic energy of each atom or kinetic energy per atom decreases by this quantity, which is an increase in chemical potential. Now let me remind you of elementary mechanics. When a particle moves from one point to another, the increase in kinetic energy is given by what? When a particle is moving, what is the increase in its kinetic energy?
Decrease in its potential.
Well, it's decrease in its potential energy if, of course, it's a conservative system. Right, but here you see that, right? Here the superfluid atoms are moving from A to B. As a result, the kinetic energy of each superfluid atom is decreasing by this quantity, mu B minus mu A, which is the increase in chemical potential. So this helps us to identify, with analogy from mechanics, that mu plays the role of potential energy here. Okay? So this helps us to end up with identification that when we write down the Schrodinger equation for an effective point particle for each particle, remember this is the wave function which every particle in the condenser obeys, a one particle wave function. And therefore, the effective potential here should be basically the potential which guides the motion of superfluid atoms. And we have already seen that the increase in kinetic energy equals a decrease in chemical potential, and therefore you should be able to identify this with the chemical potential of the particle. Okay, so this is the basic quantum mechanics equation in Landau's theory. So now, starting from this equation, Landau developed a quantum mechanical understanding of superfluid flow, and also he could actually use this to put the two-fluid model on the strong footing. And the starting of point here is basically the same thing that we had done before. Psi is psi 0 to the I theta. And now, what Landau did was, instead of just looking at the current, what he did was take a look at this wave function, plug it in here, and see what equation comes out. So you have del psi del t on this side. So what is del psi del t now? It's obviously, if you use this, it's going to be del psi 0 del t. It's about I theta. That's psi 0, I del theta del t. Into the I theta. Right? Or del psi 0 del t plus I psi 0 del theta del t to the I theta. So what the aim here is to actually put in this form in the Schrodinger-like equation that we have. Okay, in the Schrodinger equation that we have here. And there, ultimately equate the real and imaginary parts of both sides of the equation. That's what we are trying to do. So that's del psi del t. So how do you calculate Laplacian psi? With psi equal to psi 0 to the I theta. Well, so what is the Laplacian in terms of more elementary derivatives or elementary operations?
Del square del x square psi plus del square del
No,
y
that's
square
true.
psi.
Also true. And the other way of looking at that is divergence of grad, right? Same thing. Divergence of grad psi is del 2 psi del x2 plus del 2 psi del y2, etc. Now, this helps us to calculate this grad Laplacian of psi in terms of psi 0 and theta by breaking it up in two steps. First, let's look at the gradient. Now, this is a gradient of a product of two scalar functions, psi 0 and e to the I theta. And for that, we have very simple rules that you just differentiate. Like you just use rules like ordinary differentiation. Grad of it is the I theta, and that's I grad theta is the I theta. Right? I hope everybody is familiar with these basic equations of vector analysis. In fact, you should appreciate that these two equations, del psi del t equals del psi del t plus I psi del t e to the I theta, and grad of psi 0 e to the I theta, grad of psi looks like this. They're very, very similar equations. Here you have del t, there you have grad. That's it. Okay. But we don't stop here. We have to take the Laplacian. Anybody remember what is the Laplacian of a function times a vector field? Because that's what we need, right? Here, this is the function, this is the vector field. So anybody remember, sorry, not the Laplacian, the divergence, that's what we need to do now, right? We have already taken the gradient. We need to take the divergence of this. Anybody remember the formula for this?
So phi times divergence of A
Good.
plus grad phi times A
Dot, not times.
dot A.
This one is times. That one is specifically dot product, right? After all, grad phi is already a vector field. So you have to take a dot product with A to get the scalar field, which the divergence yields. Now, the divergence of this quantity. So I need to take a divergence of this theta plus this dotted with gradient of this. So divergence of this, what's that? Laplacian phi 0. Grad phi 0 plus I phi 0 Laplacian theta. But is that all? Theta is the divergence of this. But you yes. I mean the divergence
So your
of
screen
this
froze.
square bracket. Is it even now? Can you see my moving? No?
No, sir.
Now? It's still frozen.
No, sir.
Okay. I was asking if I take the divergence of this, I get divergence of this plus the divergence of this thing. So I have Laplacian psi 0 plus I psi 0 Laplacian theta, but is that all? Or do we need to get something else? Of course, we have one more term which is this dotted with gradient of this, but we are not talking about that. And divergence of this bracket, is it completely calculated or do we do something completely calculated or do we do something more?
There is this one more term. Hi. Grad psi 0
I,
dot.
grad psi 0, exactly. Dot grad theta. Because this here also we are just the same rule. Psi scalar times grad theta. Psi 0 times divergence of this, psi 0 times with grad theta. But now, in addition to this, you of course have this term grad psi 0 as I psi 0 grad theta dotted with the gradient of into the I theta, which is I grad theta, the I theta. So take the I theta common out of the whole thing. Get Laplacian psi 0 plus what? I psi 0 Laplacian theta plus twice I grad psi 0, dot grad theta. Twice because one term is here, the other term is this. Minus. What is the last term that we have in addition to this? Yes. Final term here. Is there any more terms? Are there terms here? So I've taken this. I've taken this here and here. Taken this one and this one. So of course there's one more term. And what is that?
I square grad 0 grad theta square.
So I squared is, that's actually very important for us because that's real. So the real, remember we have to couple the real parts with the imaginary parts. Minus psi 0 and what is that?
Grad theta square.
Yeah, it's grad theta square in the sense, not square of grad theta or grad theta dot grad theta. Not Laplacian of course. So now, when you have both these things calculated, you can put them together and write minus h cross square by twice n. Laplacian psi 0 is I psi 0 Laplacian theta is twice I grad psi 0 dot grad theta minus psi 0 grad theta square plus mu psi 0 equals I h cross time derivative. This. Of course, every one of these terms has an overall e to the I theta factor, which being an exponential can never vanish, so we can simply cancel that out. Okay? So everybody clear with this part of the calculation?
Yes, sir.
So now, I wanted to tell you exactly what the real part of both sides of this equation will be. Starting from the right. On this side, what is the real part?
Minus h cross del theta del t psi 0.
Good. What about the right-hand side? You of course get
Minus h
minus
cross
h
by
plus
2.
by 2m Laplacian theta. Sorry, Laplacian psi 0. Then
H cross by 2m.
h cross square by 2m. Then psi naught grad theta whole square. That's important. And plus mu psi naught. Right?
Yes, sir.
That's the real part. Of course, the imaginary part will also give us another equation, but right now let's focus on the real part of this equation. This is, of course, nothing but a Schrodinger equation. We have just written the real part of it separately. And what does the real part translate to? Basically, you divide through by psi 0 and drop the minus sign. What you get is h cos square by twice n. Laplacian psi 0 by psi 0. That's the only term which has psi 0 left in the whole thing. After the division, that is. Okay. Sorry, I made a mistake here. These two terms should be minus, right? Now, let's try to interpret these. This is just quantum mechanics, just uh, the real part of the Schrodinger equation. In fact, this would be the real part equation for any system. Usually, it's not so useful to rewrite the Schrodinger equation, its real and imaginary parts, for the simple reason that, as you can see, it's a coupled equation. It has both psi and theta rolled into it. And now let's interpret different terms here. Psi 0 is actually square root of n, right? The number of particles in unit volume. Remember, that's the interpretation we have of this macroscopic wave function. Its mod square gives us the number of particles in unit volume, and not the probability density, but it's the probability density per particle. But if you multiply that by total number of particles inside, that's exactly how it's normalized. So this is Laplacian root n of superfluid. Of course, Psi0 only describes the superfluid component, not all the particles. So small m stands for all the particles. Small ns is the density of the superfluid particles, right? This is the first term. Well, that's going to be useful only in the sense that we know that we are talking of a superfluid, which is a fluid, but a specific kind of fluid. There are two basic kinds of fluids that we have, right? Liquids and gases. And helium, of course, is a liquid. And in a liquid, the density hardly changes, right? Unlike in a gas, where the density can change very strongly with various external parameters, in a liquid, on the other hand, molecules are already very close to each other. The density is almost a constant. Is it okay?
Yes, sir.
So that's what we mean when we say fluids. Liquids are at least relatively incompressible. They cannot change their density that much. And when we say that, that's about all the atoms, right? It's small n hardly changes. What about ns? There also, the issue is the number of atoms which are in the superfluid fraction. That changes with temperature. And we have a good experimental and as well as theoretical way of understanding that. But as long as the temperature of a fluid, of the superfluid is fixed, the fraction of atoms which are in the superfluid state is also fixed. So if small n hardly changes as the liquid moves from one place to another, ns, which is the fraction of the atoms which are in the superfluid, that will also change very little. So this term is almost zero. Okay, so in what follows, we are going to neglect this term. That's an approximation. But given the fact that superfluid helium is a liquid, it's a decent approximation. Is that okay? So there are three terms on the right. One of these terms can be sort of forgotten about because ns is almost fixed. So is square root of ns, and is Laplacian, which basically has second derivatives of it, will be very much smaller than its value. So this ratio will be nearly zero. Is this okay with everybody?
Yes.
Now comes the really tricky part. Can you identify what this quantity is physically from what we have already said about gradient of theta? Last class, what was gradient of theta interpreted as? Or rather h cross by n grad theta, what was that?
Yes.
Yeah, this is the velocity of the superfluid. So, what is this? Can anybody tell me what this is?
Half MBS.
Great. That's actually 1 by twice m. Sorry, not 1 by twice m. Okay, 1 by there is an m square vs square. So this is going to be the h cross square will cancel out, and you're just going to get minus half m vs square. Okay. right? So this is the kinetic energy term, so to speak, minus mu. So at the end of the day, after the approximation, this becomes h cross del t is minus half m ds square minus q. So this thing is beginning to look like the motion of a particle is involved somewhere, right? Remember, mu is like the potential energy, and this is like the kinetic energy. But now, on this side, you have theta. If you want to get a sort of mechanical picture out of this, something which you interpret as the equation, Newton's second law, for example, del theta del t will not be what you would want, right? You would want del v del t at least. But how do you go from theta to v? How about this is an equation for theta. It will be theta changes with t. But if you want to, the basic idea which Landau actually exploited was you can make the quantum mechanical equation, at least the real part of it, essentially look like the equation of a fluid flow without dissipation, which is how he could identify that if a large fraction of the atoms went into a single quantum state, the system will behave like a fluid which is dissipation free. So, yes, how would you go into an equation for fluid flow? That is, velocity is rate of change. How would you go there? You don't have that. You have h cross del theta del. So, what would you do? What would you do is should be obvious from the looks of from what I already have on the screen right now.
Yes, sir. Replace it with Vs into m by h cross.
Yes, into?
M by h
Sorry.
cross.
Well, actually, you can't because that's gradient of theta, not theta. Okay. But you're right in the sense that what you would do is take first in the gradient of this equation. Okay. And then use the fact that drag theta is m by h cross Vs. And in a way, that's perfect because if you take the gradient of this equation on this side, you get gradient of minus gradient mu. Note that we have already interpreted mu as potential energy. So what is minus grad mu? Yes? If mu is the potential energy, what is minus grad mu? What is the negative of the gradient of a potential energy? Again, think back at class 12 or first year physics. Take the potential energy, you take its negative gradient. What do you get? Yeah, tell me. Well, this is actually the simplest question I've asked today. So I'm pretty sure all of you know the answer. So if it sounds very simple, it could very well be the correct answer. What is minus gradient of potential energy? This reminds you of something? Are you connected? Am I connected? More important. Because I thought
So
this would
electric
be the
field.
simplest question to answer. Don't worry about the chemical potential. Just think of the fact that this is the potential energy for the system. Negative gradient of the potential energy. What is that? Yes? Come on. Don't you recognize this? That this is the force? Relationship between potential energy and the force on a particle. F is minus gravity. You must remember all that, right? Is anybody? Don't seem to be. So were you able to see what I was saying?
Yes, sir.
I think I've lost most of the audience by now. Or is the connection bad in Calcutta or something? Because here it seems to be okay. I see quite a lot of people just coming in and going out. At least I can see a message now. So this was a basic equation that derived from the Schrodinger equation, which is n del Vs del T is minus gradient, or half m can be taken out. In Vs square and my claim is this should begin to look very much like Newton's law, basically because you have something like mass times acceleration here, and this is like the force. But there is one critical step, which is, as I talked about at the very beginning of this class, this is not, mass times this partial derivative is actually not equal to the force for a fluid flow. For a fluid flow, what you must have is del Vs del T. If this were a fluid flow, you should have plus Vs dot grad acting on Vs equal to minus. If this had been the equation, we would have been happy. Clear? This would have told us that the total force acting on particles of fluid, of the superfluid as a flow, is given by negative gradient of mu. And can anybody tell me why is it that if this were true, we have not shown that yet, but if this were true, why is it that we would consider this flow to be dissipationless? Dissipationless means no energy is lost into heat or some other mode. That is, all the forces acting on the system are conservative forces. And you see why this equation, if we had found it, we have not found it yet, but if we had found it, would have told us that this is a dissipation-free system, only conservative forces.
This is superfluid.
No, look, we are trying to explain why this is a superfluid, right? We cannot start out by saying this is a superfluid, so this is dissipation-free. Landau's whole thing was, and the whole thing of this theory is, we want to explain why this motion is superfluid flow. Okay, we can't start out by saying that this is a superfluid, so it should be dissipation-free. The point is, I started out by assuming that a macroscopic number of these atoms have gone into this quantum state, and this is where what the superfluid part is. That was the assumption. And we have found that the basic equation which these particles obey in the superfluid, in this macroscopic quantum state, basically the Schrodinger equation, if you take the real part of that, you write psi as psi to the I theta, and then substitute it in the Schrodinger equation, then take the real part of that, we ultimately get an equation for the velocity of the superfluid particles, which goes like this. Or we haven't yet, we haven't shown that this is what we have, but let's say we have. Then can you show? Can you explain why this is a superfluid?
So the force here is positive.
Sorry, could you just repeat that a bit louder?
So the force here is positive. Positive.
A positive, first of all, force is a vector. Saying it's positive or negative makes no sense, right? Vectors are not necessarily positive or negative. They're in some direction. But it has to do with the force. You're right about that. What kind of force leads to dissipation-less flow? I've actually used the term. The force here, if I could show that this is actually the equation that comes out, the force is minus grad mu, which means it's a gradient of a potential energy term. In other words, it's a conservative force. Only conservative forces have gradients. In other words, if you took a loop and went all the way around the loop with the force, you would get zero. Because what you would get is d mu, mu dot minus mu dot dr would be minus d mu. And when you go around in a loop, you get the mu at the end minus the mu at the beginning, which is, of course, the same point. So you will get zero. Okay. Conservative forces are gradients of scalars. And therefore, this force being conservative, what it means is whatever kinetic energy the system loses, that goes into increasing the potential energy. The energy is not lost into heat or any other form. Okay, this is why we are so convinced that Landau's theory of a macroscopic quantum state actually corresponds to a superfluid. Okay? Because the force is conservative. The only thing is we have not yet shown that yet because we have this equation. What we have M del Vs del T plus half grad Vs square. And in order to show what this is, we will just make use of a simple vector identity. So anybody remember what this quantity is? Curl A? You may not, of course. But you don't, neither do I actually. So what I will do usually is actually work this out. This I hope everybody knows this. Curl of is K component. This is familiar to everybody, right? By everybody, I mean, I guess I'm asking the only two of you who are still here. This thing is familiar? The epsilon notation for curls and everything, for cross products?
Yes, sir.
This is epsilon K, L, and del L, A, M. Then you have to use the standard identity with epsilon products with sum over K and so on. And I will urge you to check that this actually becomes gradient of S square by 2 minus A dot grad times C. This is pretty straightforward. It's just a This can't be true. That can't be correct. Let's just see what it is, because what I'm writing is definitely wrong. Can I, okay, by the way, I was trying to say it's A dot grad times A. Can anybody tell me why this would have definitely been wrong? How would I know that this is definitely wrong? And okay, this is definitely wrong because I started with the wrong thing. This is what I really wanted, not the curl A cross curl of it. But you should have spotted that it's wrong the moment I wrote something like gradient of A square by 2, because curl A is simple. It's grad dV minus Laplacian. I just forgot that that's not what I really want. But the reason why I could have spotted that it's wrong, the result that I'm writing is wrong, obvious, is the fact that curl of linear in A. Gradient of A square by 2 is quadratic. It's a product of two A's. So it can never have that in an expression which is linear in A. We are really doing this. A cross curl of A. I'm going to rewrite that. So that will be EI AJ. Curl of A is K component. Sorry, EI epsilon IJK AJ epsilon KLM del L AM. So you have EI AJ del L AM, and this is actually delta IL delta JM minus delta IM delta JL. And now using the thing, you can easily show what the result is. You should be able to show that this is actually gradient of A square by 2 minus A dot grad A. Now that's fine, but why is that relevant for us? Theory, the result. It's relevant for us simply because if you take the Vs, curl of Vs, you're going to look at gradient of Vs square by 2 minus Vs dot grad Vs. It's just this equation used again. So your job is to check that this is what I've written here is right. That starting from this, you actually get this. But now notice why this is not useful to us. We already in the equation. Here. So get grad of Vs square by 2 in terms of Vs dot grad Vs, which is exactly what we need to complete the Eulerian derivative. But we also have this term. How much is this? Can anybody tell me? Vs cross curl of Vs? Remember, this is superfluid flow.
Zero.
Special character.
So 0.
Of course, the curl of Vs is 0, right? Which means that grad of Vs square by 2 is actually Vs dot grad Vs. This term is actually minus M Vs dot grad Vs. Because superfluid flow is in rotation, this term which I got from the gradient of the kinetic energy is actually the spatial part of the Eulerian derivative. And if you bring this to the other side, you actually get this. You just to the other side. So what we have is that the velocity of the superfluid actually obeys Newton's second law equation for fluid flow. And the force acting on that is the conservative force, no dissipative terms. So what you have is a flow which can happen without dissipation, at least for the superfluid part. Remember, all not the entire fluid. Okay. So today let us stop here. Next day we will start from the equation itself, from this equation, and try to, and of course, we'll have to figure out what the normal fluid obeys and normal part of the superfluid obeys. And using that, we are going to describe various phenomena that happen in a superfluid using the two-fluid model. But this is a theoretical understanding from quantum mechanics as to why you have a superfluid flow at all. Okay? So any questions?
Yes, sir. In
Yeah.
that previous equations, when we were equating the real and the imaginary parts, so we took the size 0 only as superfluid. There is no normal fluid present.
No, yeah, because basically the superfluid is the one which goes into this macroscopic quantum state. In other words, after all, not all the atoms go into a single macroscopic quantum state, right? It's true that all atoms obey quantum mechanics. We are not saying that all atoms don't obey quantum mechanics. But here, when you are using this psi, this wave function, you have to realize that we are talking about a very specific situation. We are saying a large number of molecules, a macroscopically large number of molecules, just like in DEC, but interacting molecules in this case, have gone into a single quantum state, and that is what we call a condensate in general, in modern language. Okay? The wave function psi here, this wave function, describes only that part, the superfluid part. Remember, what we are saying is there are a large number of molecules or atoms, each in this same, described as the same wave function. And every one of these particles obey the corresponding Schrodinger-like equation. This is only for the superfluid part. So psi0 square will give you would have given you the probability density for one atom, but because we're talking of n atoms, it's basically the density of those n atoms, number density of those n atoms. But only for the superfluid part, the part which is described by this wave function.
Yes, sir.
Okay. I'm not saying that the other particles are exempt from quantum mechanics. All I'm saying is they're not in this single macroscopic state. So those are the normal atoms, or that constitutes the normal fluids. The fluids which will flow, but will have dissipation. This part, the atoms which have gone into this single state, they will flow without dissipation, is what we have just established. Okay?
Yes, sir. Yes, sir.
Okay, so this is going to be our starting off point next day, this particular equation for the superfluid part. Okay, as for the next week, I am actually a bit busy with the Olympiad camps and other things, but I will have to find a time. Is Tuesday evening okay for all of you? Okay, let's just think about it and let me know in the WhatsApp group. Okay.
Yes, sir.
Okay, so today let's call it a day now.